So now we're going to actually look and see the magnetic field's effects on both a moving charged particle, first individually, and then we're going to look over here when we're talking about a current carrying wire. Remember, a current carrying wire has moving charges moving through it, so if I put that current carrying wire inside of a magnetic field, something's going to happen. Okay? Now, I want you guys to look at the diagram on page 745 right now as I do this. What we have is we have a moving particle, we have a magnetic field, and we have the particle moving in a circular path. Okay? So remember, the magnitude of the velocity is not changing, but the direction of that velocity is changing. So what it ends up looking like is that our object starts to experience uniform circular motion, which means that there is a centripetal force acting on the particle. So now if we look here, we know the centripetal force equation, mv squared over r. Okay, we know the centripetal force equation. We also know that the only force that's acting on this particle is the magnetic force. We just did the magnetic force. In this example, we always have the velocity perpendicular to the magnetic field. So v cross b, the velocity crossed with the magnetic field, is going to be vb sine of 90, which is 1. So I can reduce that down to just v times b. So now the magnetic force, which I just got done saying, q v cross b, since the velocity and the magnetic field are perpendicular to each other, that means that this is just going to be vb times the sine of 90, which is just 1. So now I have that fb is equal to qvb. I'm not going to worry about the sign on q, so I'm actually just going to put that into an absolute value. We're not going to worry about the sign for this example. We're just doing everything in terms of magnitudes right now. This is the only force that is acting on our particle, so that means that the centripetal force must be equal to this. So qvb is equal to mv squared over r. Okay? Now we're going to do some math manipulation here because they want to come up with a nice term for the angular frequency. Okay? If we move everything around here and solve for r, now I'm going to get that r is equal to mv over qb. So I moved the r over to the other side, divided by qvb. One of the v's goes away, so I have mv over q times b. We remind ourselves that the period equation, big T, do not confuse this with Tesla. That's big T for the period. That is equal to the circumference, 2 pi r, divided by the velocity. We just found a nice term for r, so that's going to be 2 pi over v times mv over qb. Put a break right there to make sure I don't go into the next part of the lecture. And now, moving things around a little bit, it looks like I drop a v. So now I just have that the period is 2 pi m over q times b. We recall that the frequency is equal to 1 over the period. So now I have qb over 2 pi m. That 2 pi they want to get rid of because they want to have something that's called the angular frequency, okay, in radians per second. So that's going to be omega. We go back from last chapter, or last year actually. Omega is equal to 2 pi f. Or now I have 2 pi times qb over 2 pi m. 2 pi's drop out, so now I have that omega is equal to qb over m. So the angular frequency is equal to the charge, the magnetic field, and the mass. Remember how I tell you guys that they love certain things on the AP test? They love this derivation. They love the idea of combining centripetal force with the force from the magnetic field. You should be ready for it. You should feel comfortable with it. Okay? Now, I also want you guys to read 28-7. Again, this isn't too much. It's not really going to come up on the AP, but I want you guys to read 28-7, and that's all about cyclotrons and synchrotrons, okay? Not too much to worry about there, but you should take a look at it. Okay. So now we dealt with all of this in terms of a single charged particle. That diagram on page 745 gave us a nice illustration of uniform circular motion with that charged particle. Now, if we have a whole bunch of charged particles going through a current-carrying wire, the wire is actually going to bend because of that magnetic force that the current-carrying particles feel as they go through the wire, okay, the charged particles. Now, if there's no current traveling through, here I've got a magnetic field coming out of the board. Remember when we have a circle with a dot, that's like looking at the arrowhead, that's the magnetic field coming out of the board, okay? And right here, since we have no current, that means we have no moving charge carriers. That means that we have no magnetic force in this problem. However, if we start having a current going up, so starting at the bottom and going up through this wire, the wire will actually bend. And the bending of the wire is going to be outward like this. So right now we have the current traveling up. We still have the magnetic field coming out of the board. Now let's make sense of this with our cross product, okay? QV cross B, okay? This is another reason why we think about the movement of positive charge carriers. So we don't have to worry about the negative sign on this right now. So V cross B. V is in the direction of those moving charge carriers, so that's moving up. We want to do V cross B, okay? B's coming out of the board. Point your fingers in the direction of V. Curl your fingers toward B, which is coming out of the board. So we have a force on this wire that's going to try to bend the wire to the right. If I have the current traveling in the opposite direction, it should be obvious at this point, okay? Current traveling in the opposite direction, we get a bending the other way. So now we have the current traveling down like that, B, B, B. Now we have V traveling downward. We want to point downward, curl our fingers toward B, which is still coming out of the board, and we feel a force that is to the left. So here we had a force to the right. Here we have a force to the left. FB, starting with the FB. Okay? Now let's actually try to see if we can make sense of that a little bit and figure out what the quantities are going to look like. We know that the amount of charge is equal to the current times the time. And we also know that that would be equal to the amount of current multiplied by L over V times D. Okay? L over V times D. Excuse me. That should be the drift velocity there. Okay? That should be the drift velocity that we talked about a few chapters ago. Okay? So if we take the amount of length of the wire and divide it by the velocity, that'll give us the time that it takes the charge carriers to go through that amount of length, and that stands for the T right there. We also know that the force from the magnetic field is equal to QV. Again, we're going to refer to this as the drift velocity, B times the sine of theta. So this is what we've learned this chapter, QV cross B. I've kept the sine of theta term inside there, okay? Now I'm going to replace the charge with IL over V times D. And I still have a V times D, B sine of 90 degrees. Again, we're considering the perpendicular case where the velocity is going to be perpendicular to the magnetic field. That makes everything very easily. We deal with the sine of 90 right there. It goes to 1. And then I have VB is equal to ILB. ILB. And this is for the case when B is perpendicular to L, the wire. Back up here, I said that they met at 90 degrees, so this is for the special case when B is perpendicular to the wire. Now we got to remember something here. Current is not a vector quantity. So we're actually making a vector out of this guy right here, L. So now what I have is that FB, the vector, is equal to I, L cross B. And L is in the direction of I. The length vector that we're going to use in this case is in the direction of the current I. Okay? So again, this chapter is just a lot of derivation. It's just a lot of plug and chug. You really want to be clear on your cross products. I want to see you guys definitely using your right-hand rules to see how everything's being manipulated. But there really isn't too much to this chapter. It's not that bad. When I get back, we will go over the magnetic dipole moment. We'll finish that up on Monday, and I will answer any and all questions on this material. Best thing you can do for this stuff is read the chapter. However, the stronger you guys feel about the magnetic fields, the better you're going to feel as we move into the next couple chapters.